The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, and welcome to Lab Manager's Tech Trends webinar series. I'm Tanuja Kopal, contributing editor for Lab Manager, and I will be moderating today's discussion where we will be focusing on innovations in FTIR, which stands for Fourier Transform Infrared Spectroscopy, and some of its emerging applications. We are joined today by two technical experts from Agilent Technologies and PerkinElmer, who will be talking about some of the new features on the latest FTIR instruments and also talking about analysis and applications that have been made possible by some of those improvisations. Our discussions in these webinars tend to be very interactive and informal, so please feel free to send in your questions or comments anytime during the webinar, and we will discuss them right after our speakers have gone over their brief presentations. You can type in your questions in the question box that appears on the right-hand side of your screen, and I will be receiving it on my end. Today's webinar will also be available for viewing on Lab Manager's website, which is www.labmanager.com. The website also hosts a number of resources such as application notes, white papers, links to past webinars, a list of our upcoming webinars, and you may find some of that very useful. In our closing slide, we will also share with you the email addresses of our speakers, so you can reach out to them for a copy of their slides or for further guidance on this topic. You will not be able to download a copy of the slides from our website. So with that, let me introduce our first speaker today, who is Dr. Mustafa Kansiz, who is currently a FTIR product specialist at Agilent Technologies. He has over 15 years of experience working with FTIR, spanning everything from routine to research applications in both industry and academia. He has spent the last 7 years with Agilent Technologies in a range of technical and business development roles, and his current responsibilities include applications development, marketing, and new product development. Welcome, Mustafa.
Thank you for the introduction, and thank you for everybody for attending. I thought I'd start off the presentation by giving a reminder as to what FTIR spectroscopy is in case anybody is not so familiar. And essentially, Fourier FTIR stands for Fourier Transform Infrared Spectroscopy, and is essentially the interaction of infrared light with matter, with the vibrations of bonds between atoms in a molecule being excited by IR light. This leads to absorbances that are specific to the chemical structure of the sample under analysis. And on the screen there I've got one particular example of a spectrum, and this is of nylon. And we've also highlighted some of the key peaks and what they belong to. For example, the NH stretch, CH stretch, carbonyl bands. These are all assigned to functional groups of the molecule and are specific to that particular molecule. And hence it is this feature, this attribute, that really makes as this specificity that has made FTIR applications possible for identification and confirmation. So why would you be using FTIR? Why should I use it? Well, FTIR is one of these workhorse analytical methods. This is how I put it. Virtually all labs have one and probably need one if they don't have one. And the key to this is the versatility. It can virtually measure any sample type or size or form, from solids, including your powders, pellets, solid blocks, or even your finger, liquids, from organics to aqueous-based samples, and gases. Pretty much the only thing it cannot measure are metals, so this is a molecular technique and not an atomic technique. The other key benefits here are the fact that it's non-destructive, there's no sample preparation, and the key to this has been the ATR sampling technique, attenuated total reflectance. It's qualitative, which is a very traditional approach to FTIR or use of FTIR, but it's also extremely quantitative as well, and that's something that really should not be overlooked. It's simple to perform, again, through a lot of these newer accessories. It's very accurate, fast, taking only typically seconds, and it has become increasingly affordable. So I thought I'd start off by introducing Agilent Technologies, the company. It's a multi-billion-dollar company with revenues almost at $7 billion, and it is essentially split into three categories: the electronic measurements, chemical analysis, and life sciences group, with FTIR fitting across chemical and life sciences group, addressing a whole host of markers from food safety to pharmaceuticals to materials, forensics, etc., with a whole host of product lines to complement FTIR, chromatography, mass spectrometry, molecular, atomic, and FTIR fits into molecular, of course. Next. The background of FTIR and Agilent really stems from the fact that there is a long history there. The innovation goes back to 40 years to Block Engineering, who were the pioneers in FTIR. They released the first commercial FTIR back in 1969. Since then, the product line has evolved through various names, through Bio-Rad, Digilab, and some of your users may be familiar with FTIR from Bio-Rad and Digilabs, onto Varian, culminating in the acquisition of Varian by Agilent in 2010. And really throughout its long history of this product line, it has been at the leading edge of technology with many firsts, such as the first MCT, first FTIR microscope, and the first chemical imaging system back in 2002. This history of innovation has continued more recently with the acquisition of A2 Technologies and the subsequent release of the 630, now the world's smallest FTIR. And I'll be talking about that next soon. The Agilent's FTIR portfolio is quite extensive and services a range of users, from your mobiles, your routine, through laboratory research, and up to our flagship microscopy and chemical imaging products. Of particular interest is the 630 that I'll be giving one example from, with its new innovative dial path liquid sampling technology. I'll be talking about our research instruments and some applications there centered on the 670 with its 400% higher throughput, and I'll be finishing off with a chemical imaging application as well. The Carey 630 was released in 2011 and is a great example of how innovation in instrumentation and in particular sampling accessories can help change for the better many different routine FTIR measurements. Perhaps the most exciting aspect of the 630 is the unique and innovative dial path accessory. Well, what is a dial path accessory, I hear you saying? For me, this is really a new and revolutionary way to measure liquids. If you think about traditional methods of measuring liquids, at least in a variable sense, one would have to use a traditional demountable liquid cell, as I've pictured in the bottom left-hand corner here, where in order to change the length, the path length, you had to demount it, take the spacer out, put it back together. And anyone who's done this knows this is extremely tedious and fraught with risks in terms of leakage, blockage, breakage. It's a very, very difficult thing to do. All of this has been replaced by a simple three-step procedure using the new dial path, which, if you can see on the top side there, top picture, there's a position 1, 2, 3 on the dial. Each one of these positions has a different but fixed path length, and the path lengths can range anywhere from as little as 30 microns, which is perfect for neat solutions, all the way up to 200 microns for your lower level analytes. And the process essentially consists of cleaning the crystal, putting a drop on the crystal, and then rotating the dial path into the required position, position 1, 2, or 3, depending on what path length you need. And an example of this is the measurement of toluene and some of the low-level impurities in toluene. In the bottom right-hand corner, we can see 3 spectra, each collected in 8 seconds, used at 50 microns, 100 microns, and 200 microns. And we can see how some of the very low-level impurity bands get stronger and stronger, of course, with the longer path lengths, leading to better quantification. And what are some of the benefits here to the customers, to users? It removes risks of bubbles, it makes liquid sampling far easier, and it enables a wide range of concentrations to be measured without having to worry about serial dilutions and the like. So that's one example of a routine application that makes life easier. I'll move on to some of our research spectrometers, our flagship research spectrometers, and my catchphrase here is really power to measure difficult samples, and I'll be focusing on our 670 instruments. Most FTIR measurements, especially the more research type measurements, are using accessories nowadays. These include ATRs, often diamond ATRs. Could be heated diffuse reflectance accessories for catalysis research, absorption, desorption processes. Fiber optics are commonplace, and even coupling to custom accessories and optics such as ultra-vacuum chambers for looking at plasma gas, for example. All of these accessories or couplings are typically very low throughput, and in order to regain some of those losses you need a very, very powerful instrument, and certainly the 670 is that with its 400% higher throughput than any other research instrument. In fact, it's so high that we cannot measure a simple transmission sample without attenuating the beam by 75%. Some of the with research experiments, typically also instrument limits are pushed as well in terms of your sensitivity, your throughput, spectral resolution, and kinetics rate, so that's spectra per second. And I'll show you a couple of examples of where sensitivity and kinetics rates have really made a difficult experiment relatively easy. The first one is the photochemistry of a cyclopentene rhenium complex. And in this case we've done a UV photolysis of the complex, leading to an intermediate formation whereby one of the COs are dropped off and replaced by a solvent. That very quickly falls off and forms a dimer, and this can be monitored in real time. On the next slide here we can see on the left hand side a different spectrum. The blue here is at 9 milliseconds, which is a spectrum or a different spectrum of the intermediate, and then the red we have 150 millisecond time slice, which is now the dimer. And because of the high time resolution, it's actually very easy to measure the pure spectrum of that fleeting intermediate complex. In the bottom right hand corner we've actually plotted the peak areas related to the intermediate product in blue and the dimer formation in red. And you can see that at laser initiation there is an almost instantaneous appearance of your intermediate product, which then dies off with a half-life of around 50 milliseconds. All of this, and this really demonstrates how detailed information about reaction kinetics can be obtained with ultra-high kinetics rates with only one scan averaged. And again, this comes back to the 4x throughput of the 670. Bear in mind that these differences here are in the milliabsorbance range as well. The second demonstration of a difficult sample made easy is a model system. In this case, this model here is ethanol and water with a ATR measurement, a single bounce diamond ATR. And traditionally, aqueous samples for low analyte concentrations are viewed as difficult, primarily because your ATR is relatively low throughput, anywhere from maybe 10 to 20% throughput, and water itself can be a very difficult matrix as well. On the right-hand side, we see that we have a 1% spectrum, and in blue down here we have a 0.1% spectrum. And the LO, the limits of detection, have been estimated to be 500 ppm. But the most amazing thing for me here is this is with a 5-second measurements using a standard room temperature detector and a single bounce ATR. Significant lowerings of limits of detection can be achieved by using an MCT detector, for example, a multi-bounce ATR, or a longer collection time. I'll move on to the last section of my talk, and that's microscopes and chemical imaging. The catchphrase here for me is simultaneous chemical and spatial information. So why use an FTIR microscope? Well, an FTIR microscope has essentially two main purposes. One, it allows users to visually see small micron samples, and two, allows users to collect spectra from these samples. Excuse me. And microscopy can be performed in essentially 4 modes: single point mapping, linear array mapping, and focal plane array imaging. And it's really on that last point, which is what Agilent does, that I'll focus on. And if there's one take-home message you take away from this that summarizes what chemical imaging is, It really gives you the spatial information, the where, and it gives you the spectral information, the what. But it gives this simultaneously. This is due to the two-dimensional focal plane array that is at the heart of any chemical imaging system. Next slide. So here's a review of how these various modes work. A single point takes one spectrum from one spot, and that's it. A mapping experiment is an automated acquisition of grids, and thereby you can build up a contour map of your sample based on a particular absorbance. The third, linear array mapping, uses a line of detectors, typically 16 in a row, still requires a mapping approach to raster across the sample. And the fourth is the two-dimensional focal plane array imaging, which captures, it's essentially a digital camera or a chemical camera capturing spectra from across your sample simultaneously. And these focal plane array-based imaging measurements are up to 50 times faster than linear array-based systems, and certainly many hundreds of times faster than single-point mapping. So what does this allow us? What does this make? What can we do that might otherwise be difficult or impossible? Well, one of my favorite applications is the sample preparation-free chemical imaging of polymer laminates and films. And how laminates and films would have been measured in the past would be you need to embed these in resin, cure them overnight, cut and polish them, and then do FTIR imaging with them. That's been replaced now with a novel method we've developed, which essentially consists of cutting out a sample. In this case, in the picture here is a sausage wrapper, placing it in the sample holder, simply cutting it by hand with a razor, and then placing that into your microscope stage and raising it to touch the FTIR crystal. And that's what this laminate looks like, cut, as I've just done, as I've shown in the previous slide, with the FTIR field of view being 70 by 70 microns. So this is a microscope FTIR through which we will do chemical imaging, where each pixel will measure an area of about 1 micron. And the results? Well, these are the chemical images and extracted spectra. So this happens simultaneously and is about a 30-second measurement. And we can see that multiple layers have been identified. On the left and right sides, identified here in green, is polyethylene. That's clear and that's relatively easy. In the middle, we have nylon, again at around 16 microns. That's relatively easy to see. But the real power here is the ability to measure these really thin adhesive layers between these main layers. For example, a polyurethane layer of only 2 to 3 microns thick. And I'll remind you that this again is with virtually no sample preparation, no resin embedding. From the point of having the sausage wrapper in your hand until the chemical image is created is about 5 minutes. So I'll finish off with a summary to say that Agilent provides a full range of FTIR solutions addressing various markets and applications, covering products from handheld and mobiles, your routine laboratory, research instruments, and FTIR chemical instruments. And where do we see some of the future trends? Well, I think the trend towards miniaturization will continue, and the move towards more mobile FTIR measurements will continue. Certainly simplified software and more turnkey applications as users become less and less experts. The software will need to cater for that. And I also expect to see continued growth in FTIR imaging. And this is really due, I believe, to the unique simultaneous and spatial and chemical capabilities that are used to gain better insight into diverse applications, such as polymers and materials, into biomedical research, which is very exciting, through to forensics and geological studies. The number of applications are almost endless. And with that, I'll finish off on my contact slide with my own email there and a couple of interesting links. And I'll throw it back to the organizer. And I thank you for your time and for your interest.
Thank you, Mustafa. I would like to remind those of you who joined us a little late that today's webinar will be available for viewing on Lab Manager's website for at least 6 months. The link to the archive webinar will be emailed to all of you sometime next week, and the email addresses of our speakers will be shown on your screen in our final slide. So please feel free to get in touch with them directly if you're looking for a copy of their slides, because you will not be able to download any slides from our website. Our second and final speaker today is Sam White, who is the senior-most infrared, near-infrared, and Raman product specialist in the Analytical Sciences and Laboratory Services group at PerkinElmer. His work involves infrared analysis of standard samples, chemometric analysis of mid and near IR samples, Raman microspectroscopy, programming methods for repeated analysis, and he's also involved with consulting and training for FDA Part 11 and Part 111. His current responsibilities include assisting sales, generating application notes, and competitive analysis information and customer training. Welcome, Sam.
Hello, everyone. This morning I will be speaking about infrared microspectroscopy. I can get the first slide. Why an infrared microscope? And Mustafa covered some of this, but a single beam condenser will do pretty much what an infrared microscope, but with one major exception. You will not be able to see the sample. So an infrared microscope allows you to visually inspect the sample and then analyze that portion of the sample that you're interested in. Often you must isolate the area of interest. The sample is very complex, and so apertures or other devices are used. You can also measure in both transmission, reflection, and attenuated total reflectance, which I'll talk about later. And you can measure in either just a single spectrum or with maps or line scans and present the data a lot of different ways. So what can an infrared microscope do? Traditionally, we would say that you can see particles down to 10 by 10 microns. They can be fibers, particles, crystals, paint chip, whatever you can dream up, basically. Now, there are some samples that are large, but they have contaminants like paper, polymers, electronic components as well. You can do surface chemistries, surface defects on paints. That's very common. Or the change in the composition of purity of materials, and so much more. So what is an infrared microscope? And I should point out down at the lower left is the original infrared microscope. That is the Model 85. It was introduced by PerkinElmer in 1968, a little before my time. Okay, on the left is a stick diagram, if you will, of a visible microscope. The stage is where my cursor is at the moment. And that's taken out for brevity and clarity. We take a normal tungsten light for most visible work. We come through a condenser, which is some sort of probably multi-component optical glass components, and then to an objective, which is always a complex compound glass objective with coatings on them, up to the eyepiece, which again probably is one or two coatings and some sort of anti-reflection coating on it as well, and then at least traditionally up to the eye. Lately it's been to CTD cameras, but your eye is what you visualize most. On the right side is the infrared microscope. So there are two things in the visible microscope that keep us from using it in infrared. The first is your eye. Your eye cannot see infrared. So we must have a detector that can see infrared, and that's usually a mercury cadmium telluride liquid nitrogen cooled, what we call an MCT detector. The other thing is glass. The objectives in a visible microscope are made out of glass. Glass does not transmit infrared, so we cannot use glass optics. To get around that, all the manufacturers use what are called Cassegrains or Schwarzschild objectives. They're basically a big primary mirror and a secondary mirror, which pass light from the source, which in this case, the source would be the infrared FTIR, up to the lower condenser to the sample. What is not absorbed by the sample is then transmitted up to the second Cassegrain, through slits if you're doing point mode, through a third Cassegrain, and then focused on the detector. The magnification is a little different. The magnification infrared is basically 1. We try to re-image the sample at the detector, which is a little different than the microscope, where you have to make things bigger for your eye. Now, as I said, there are 3 modes you can operate in. This is the transmission mode, where light comes from the spectrometer to a toroid, down to a pickoff mirror, to the bottom Cassegrain, up to where the sample position would be. And what, again, is not absorbed by the sample is then transmitted up to either the camera or, in this case, to the detector. So that's transmission mode. In reflection mode, we just relocate the mirror to another pickoff, and the bottom Cassegrain is not, or the condenser is not used at all. So we bring the light up to the pickoff mirror, and then it comes down to the sample. Now, you only have one optic there, so the way this has to be done is on the right, where you bring the light in on one side and then collect on the other. The light, again, then just either goes up to the camera or to the MCT detector. So in theory, you should get half as much throughput with reflection as you do with transmission. Frankly, these days, I don't see it that often. It's about the same, even though theoretically it's true. So how do we run a sample? Well, the most difficult part of running a sample is actually finding the sample. There are a lot of tricks involved in that, and if you had a high school or college chemistry or biology, they probably showed you how to find a sample. But here is a sample that I have found. It's on a barium fluoride window. Barium fluoride will transmit infrared. And I have now focused it. The red box you see is where the current aperture, and that would be the size of the detector, which is 100 by 100 microns. So the next thing I have to do is decide how much of the sample or what portion of the sample I want to measure. So I've made the aperture smaller to about 40 by 40 microns. So that's the place, the position, and the size that I will measure. The next thing I have to do, because all FTIRs are single beam instruments, is I must do a background. So I move the instrument off the sample, find hopefully a clean spot on the window, and perform my background with the same aperture. Then I move the sample back to the stage back to the sample, perform a scan, and in a very few seconds I get a spectrum. And anybody that's ever done infrared microspectroscopy should know what this is. This is the most common contaminant in infrared microspectroscopy. This is the spectrum of skin. Looks a lot like the previous slide of nylon, and it sort of is and it sort of isn't. But that's a very, very common and very, very easy sample to run. Traditionally, that's about 95% of what people do with infrared microscopes. They find a sample, usually they spend some time under a stereoscope picking out the area of interest. They put it on a window that transmits infrared, and they get a spectrum. But there is another area where we use more than one detector, and that's called imaging. Now, you heard about the focal plane array. PerkinElmer uses a linear array, a 16 by 1 linear array. We do that for several reasons. One is sensitivity, and one is range. But the important take-home message here is the more detectors you have to a point, the larger sample you can image or scan in a very short amount of time. So here's an example of a fly's wing, and on the upper presentation you see what's called a false color image. Again, your eye cannot see infrared. So this is, we convert the infrared into visible so that you can see it. So this shows you a reasonably large fly's wing. I believe it's 18.5 by 4.5 millimeters in diameter, and it has about 60,000 spectra in it. Now, the spectra in the fly's wing are not particularly exciting, chemically speaking. They're all basically a protein of nature or chitin. But this does show you the size that you can image, and in the bottom the spectra shows you the spectra you would obtain. And again, there are 60,000 spectra in this particular image. Another example that I do often, and one that most people can relate to, is take a dollar bill. This is a picture of George Washington on the face of the dollar bill. This is a rather large image. If you look at it, the red box on the left shows you the area that we analyzed. And on the right is the chemical image. So the dark areas on the right tell you that that's ink, and that is the chemical information of the visible image on the left. And that's what chemical imaging is. You see the visible image and the chemical image. Sometimes they look the same, and sometimes it's quite surprising what you see. So I'll go through a couple, 3 applications here, and then we'll be done. The first one, I'm 70 years old, so this is sort of interesting to me. This is research on rabbit arteries. And on the left, again, you see the visible image. And on the right, you see what's called the false color image. Now, it doesn't look all that much different than the visible image because basically it's just the total amount of energy hitting the detector. Sorry, my phone's ringing. If we do chemical imaging, though, you can see that there are 2 chemical species here. There is, of course, the artery wall, which is, of course, protein. And then there is cholesterol plaque that's built up on the side of the artery. Another adaptation to infrared microspectroscopy imaging is ATR. Sorry, my fax machine's working. ATR microscopy. The advantage of doing ATR imaging, this is internal reflectance, if you will, is first of all, the sample is very, very easy to prepare. All you have to do is flatten the sample somewhat. You can embed it if you have to, but you don't. It's not necessarily required. The other thing that's very important is that you only see the surface, a micron or 2 into the sample. So the advantage of that is you don't get the complex problems that you get when you try to do transmission reflections, which I'll show in the next slide. So here's an example of 2 or 3 ways that we do infrared imaging. The transmission way, normally we slice the sample if we can to about 6 microns in thickness. And in the top presentation, that looks great. But if you look at a real sample, you'll see that the real sample has lots of little particles in it. And if we're interested in one of those little particles, the thicker the sample, unfortunately, the more likely we are to blur the image. Now, a lot of the people that do a biological analysis will take a tissue slicer, slice their tissues, and put them on a glass slide that's coated with basically silver. Now, you can go to Home Depot and buy low emissivity glass, and that's basically what this is. It's, for all intents and purposes, an infrared mirror, but visible light passes through it, and it's very popular for the tissue people that want to do biology and infrared at the same time. The problem with that technique is you do a double pass through the sample because the bottom is an infrared mirror. And if you have these same particles, the blurring is even more pronounced. By ATR internal reflectance, we only see a micron into the sample. So whatever touching the face of that crystal and only a micron or 2 in, we get an image of. So the spatial resolution is improved dramatically. So here's an example. Up on the top is the PerkinElmer Spotlight 400 imaging microscope. And this is a section of a renal stone. And I'll just click here and show you kind of how the sample is imaged. The array moves across the sample and then across the other part of the sample. And that is the way the map is generated. And the lower left shows the actual device. It's not on the stage. It's just for clarity. The sample is usually mounted on this little platen. And it just has to be flat and kind of stick to it. You put it on the stage here, align it, and then put the vise on and clamp it down. The advantage, again, is the spatial resolution now becomes 1.56, which is dramatically better than either transmission or reflectance. So here's an example. This is an old one, photographic film with multiple layers on it. And starting at the edge, you get a gelatin layer. The gelatin layers contain all the pigments, if you will, or the things that are photosensitive. And then towards the end of the film, you get the support layers of polyvinyl acetate. Now the way this works is, if you picture down at the lower left where my cursor is, that's where the sample would be, and we would take a scan and get 16 spectra. Then we would move the stage a little bit and now take another scan, get another 16, and so forth. It may sound tedious, but at 170 scans a second, it doesn't take long. Here are some examples which could be of some use. This is a renal stone. It's a kidney biopsy, if you will, and the visible image is on the left. And these little dark areas here are the actual stones, if you will, or rocks or inorganics that are in the kidney. Now, if you look at them under transmission reflection, which is using a low-E glass, first of all, you see this middle presentation where you kind of see a kind of a blurring, a little blob there. And if you look at the spectra, yeah, you got nylon and you get carbonate, but it's really pretty hard to see. But by ATR imaging, you can clearly see quite a bit of detail within these stones, and the spectra are much, much, much easier to identify and much, much better. And then finally, this is a detector we're working on, should be introduced sometime in late fall or at the latest early next year. One of the problems with the focal plane array and even with the PerkinElmer linear array is scan range. Our instrument goes down to about 720 wave numbers, and that's okay for most applications. But for some things, and in this case, we're again working, this happens to be a section of a tooth, and the researchers are very interested in the phosphate layer of the tooth. Now, traditionally, what is done is you look at the peak around 1100 to 1000 wave numbers. But the problem is that peak is very, very big and in a nonlinear area. So while it's usable, it's not the peak that most people would want to use. Traditionally, what they like to use is a peak at 580, which is a crystalline doublet that has to do with phosphate. The new detector that we offer will scan down to about 550 wave numbers, and this is just an image of a tooth, a section of a tooth. On the right, you see the protein layer of the tooth, and on the right side, you see the phosphate layer. Quite an interesting image. So that is my talk. I want to go a little bit on PerkinElmer. In the upper left-hand corner is a Spectrum 2. That's our newest instrument, low-cost instrument. It comes with a lot of features to it. It is a transportable instrument. It can be operated wirelessly. We have a little travel pack for it. Also, there are a lot of canned applications that can be done with what we call the touch software, where all you have to do is actually, if you have a touch screen on your computer, just push it and it'll give you the answer. On the right is the PerkinElmer Frontier. It's both a mid-infrared, near-infrared, and or a far-infrared instrument. It's very, very, very flexible in what it can do. And in this configuration, in the sample compartment, we have a single bounce diamond ATR, and on the right side, you have a near-infrared integrating sphere. And then on the bottom left is the Spotlight 400. Although all the Spotlights, we have 3 of them, look about the same, the major difference is the Spotlight 150 and 200 are single-point detection systems. The Spotlight 400 has both a single point and an linear imaging array. I want to stress again, PerkinElmer has been in the business for 75 years. It's our 75th year as a company. And if you need some application information or just product overuse, the links are here, and you're welcome to either contact me directly or just go to these different websites and download what you want. Thank you very much, and I'll turn it back to the presenter.
Thank you, Sam. We already have some questions that have been sent in, but remember, if you have additional questions, you can always send them in by typing it into the question box on your screen. And now you also see the email addresses for our 2 speakers. Feel free to reach out to them if you need a copy of their presentations or if you have additional questions after the webinar. So let's start with the question about size range. I know both of you commented on this during your talk, but can you reiterate what is the size range that is possible to see using FTIR microscopes?
If I may start, the size range, there really is no limit. It can just depend on how whether you have an automated stage or automated stages will give you up to 3 by 5 inches, at least in our system, of travel. The question is really what sort of spatial resolution, what sort of magnification is required, and that can range anywhere from sort of 1 micron at the ATR level up to, in our case, we can do 19 microns per pixel.
Okay.
And the time required. So some of these larger collects can take a fair bit of time.
Okay. Sam, what about the, yeah, go ahead.
Basically, I would agree. The size of the image, if you're in transmission mode or reflection mode, is the span of your stage. The standard stage is pretty much the same as the Agilent. We do offer a larger stage, but again, varies time, so you've got to consider that. Really, when you're talking about microscopes, you're talking about a reasonably small area. In ATR imaging, then it's the size of the crystal. Our standard crystal is 600 microns in diameter. We also offer a 1200 micron ATR crystal.
Okay. All right. Moving on to the next question. Are either of you familiar with silica analysis in air by infrared? And is there any progress in direct analysis of the PVC filter? This is somebody who's in an industrial hygiene lab, and they wanted to know more about silica analysis in air.
I did do some work many years ago with the Bureau of Mines, and that technique requires first you have to acquire the sample with one of these filters, and you have to digest the filter, and then just measure the sample in transmission mode. I'm not aware of any new methods in that regard.
Sam, I don't have any direct experience, though I'm aware of a colleague, I believe in Canada, who was telling me that the ability to actually measure these directly on the filter itself, with or without digestion. I'm not too sure if that particular person would be interested in sending me an email. I could put them in contact with somebody who could provide more info.
Oh yes, we can certainly do that. We can forward the question along to both of you actually, yeah. And if you have additional resources or if you can put them in touch with the right person, that would be great.
Sure.
Thank you. All right. The next question is about systems that use dual apertures. Are either of you familiar with those systems, and do they offer any, added advantage?
Well, there is a brand of it's not on this phone call that offers that. It's more of a competitive thing, and they will claim that there's some excitement there, but I've never seen it proven. What it does do, which is detrimental, is it increases the path length of the beam significantly, so that the moisture bands and the carbon dioxide bands and any of their perturbations in the beam are magnified by 2. So yeah, you'll hear a lot of competitive arguments on that. I don't think you'll ever see any real data.
If I essentially agree with Sam there, I will add that some of the other negatives there are significant decrease in throughput. But ultimately, why does anybody even try to use a dual aperture or a redundant aperture, as they're otherwise known? And that's to increase spatial resolution. This is really only applicable to single-point systems, and really the ultimate method to increase spatial resolution is to use an imaging system, in particular one with an ATR. So ATR imaging is really the only way to get sub-diffraction in air, at least, limited performance.
Okay. All right. A couple of questions from somebody in India who is involved with analysis of homeopathic drug solutions. So the first question is, can structural information on silica molecules present in different dilutions of homeopathic drugs be measured by FTIR?
What would be the constant? Well, you don't know. The concentrate, probably not, but we'd have to look at this in detail and get some information. Usually if something is in solution, it makes infrared a lot more difficult. And then we have to know what the concentration is, and if it's below 1%, it probably is not doable.
Okay.
Plus, you do lose that information if it goes into solution sometimes.
Yeah,
Correct.
I'd agree. I think anything in solution, if it's particularly low concentration, quantification is generally okay, but extracting structural information, because the bands are so broadened, makes for subtle structural elucidation difficult. But without actually seeing the samples and measuring them, we can't be certain either way.
Okay. And then as a follow-up to that is, can we use SEM or TEM in place of the microscopy to study nanoparticles in the homeopathic drug solutions that I use?
I'll perhaps start that one and saying that SEM and TEM are really a completely different order of magnitude, completely different technique. We must remember that with infrared spectroscopy, we're limited by the relatively long wavelength, so your diffraction limited. And if you're working with a germanium ATR, you can enhance that by maybe a factor of 4. So at best, you're looking at 2-3 microns resolution. So that will never work for nanoparticles, which is why some of these electron-based imaging techniques are the only way to look at some of these very, very small particles.
Okay.
The other thing, and I don't know much about that field, but the information you get is not very diagnostic organically. You do get the elemental information, but you don't get much of information organically, which is what infrared will do for you.
I see. And there are no specific bands or hydrogen bonds or anything like that which can be determined?
Well, we don't know. I don't know.
Okay.
I don't do
Well, what we can do is like I mentioned in the previous case, we can forward you the attendee's contact information, and maybe you can follow up with him offline to see how you can help him.
Sure.
All right. The other question is, a lot of the pharmaceutical analysis are now switching to using near-infrared or Raman scattering in place of FTIR, particularly for identity testing. Maybe one of the reasons is because FTIR, at least I think, has issues with sample prep. Could either of you comment on that?
You want me to go first?
Yeah, go Sam.
We've done an awful lot of this. It depends on the sample. In the United States, all the nutritional supplement companies are now falling under Part 111, FDA, Part 111, and they must do testing. Traditionally, a lot of the botanicals were done by near-infrared. That's where near-infrared really got its start doing sort of things like the amount of moisture and fat and protein and grain. So it was a natural thing to go to near-infrared. I don't think you'll find anybody that will say that near-infrared is the only way to do that. Historically, it can be done. It really comes down to sample load. How many samples a day are you going to run? Because near-infrared has the advantage of working through glass. You don't have to remove samples from a glass vial. The problem with near-infrared, if there is one, is it's not particularly diagnostic. You must build your own library. You must run your own samples. You must do your own identification. And the spectra you get from near-infrared are not very telling. So if you put it in a total unknown, near-infrared is not going to help you. The opposite is true in mid-infrared. If you run a sample by mid-infrared, the spectra is very diagnostic with very little education. You can tell a great deal about the makeup of the molecule. So really, when it comes to nutritional supplement, it really boils down to what's your workload and how much do you want to spend on the instrument.
I certainly agree with all of that, and the historical reasons why near-IR has been very popular in those fields. I'll add that I think perhaps in some of the more emerging markets that the advantages in the ATR technique are perhaps still not as widely accepted as they might be in some of the more Western countries. And ATR really has removed much of the issues with sample preparation, as compared to a KBR pellet or diffuse reflectance or a neutral null. It's things can be measured, of course, directly neat. You still need to take them out of the package to do ATR, though increasingly also fiber optic coupling probes, which worked very well in the near IR, are also, with advances in technology there as well, working very well in the mid IR as well. So you can in fact take an ATR tip on the end of a probe and put that into a bag of something or into a drum of some liquid. So advances in sampling technologies, I think, should go a long way to bridging the gap between the ease of sampling between mid-IR and near-IR.
Well, appreciate that feedback. What about applications that involve the combined Raman FTIR for microanalysis, particularly in areas like forensic, pharmaceuticals, and biomedical fields? Have either of you had experience with the combined Raman FTIR?
I have. I don't know how to say this. Raman is another technique that gives you information that's similar to mid-infrared. It's complementary. And about 80% of the time, you can get the same information by either technique. Raman doesn't require any sample preparation at all other than focusing onto the sample. So that's in its favor. The real problem with Raman is to do it right, you're going to have to spend some money. In the United States, that would be about $100,000, where you can get a mid-infrared to do that for under $20,000. So Raman is still trying to find a place. There are certain applications that are traditionally used. Polymorphs, for example, in the pharmaceutical business are generally done by Raman, but they can be done most of the time by mid-infrared. We do have Ramans in several forensic accounts, and they're used, but I'd be hard-pressed to say that there's a killer application for Raman.
Okay.
Yeah, well, once again, Sam, I certainly agree. I think when it comes to Raman microscopy, there are pros and cons, and one of the other pros, or perhaps of a Raman microscope system, is the small spot size and enhanced spatial resolution, but they're typically very low signal to noise. You have issues with fluorescence, which can be a real killer. So there are only a few, or most samples will have some degree of fluorescence, and they are, to get a good system, it is a relatively expensive system as well.
Okay. Actually, that brings us to the end of all our questions. I was just wondering if you could comment on, what are some of the types of improvisations that users are actually demanding, and what can we expect to see in terms of improvisations going forward?
Improvisations, you mean product developments, enhancements?
Yeah, or just changes in the instrumentation, the software, anything that people should look out for in the coming months.
Go ahead.
I was going to say, as I said in my closing slide, I'm seeing a trend to smaller instrumentation, simpler instruments, and more mobile instruments, where people aren't able to or don't want to necessarily bring a sample into the lab onto a lab-based bench. You can now have handheld FTIRs to point and shoot. One of our ExoScan FTIRs is now used to measure curing on the Boeing Dreamliner directly on the actual fuselage itself. So that's a classic example of taking the measurement to the sample, and I'm also seeing improvements required on the imaging side as well.
That's neat. Yeah. Sam, your
perspective? Yeah, I'd have to agree with that. Certainly, smaller instruments are actually demanded by customers these days. Ease of use, the single bounce ATR, which was invented years ago, but has just been widely accepted, universally accepted as the sampling technique in the mid-infrared. It's incredibly simple. We all have them. They all work very, very well. You can either go with a diamond crystal that'll last forever or something like zinc selenide or germanium that'll wear out in a couple of years. But basically that is what customers are asking for, and then of course software to be very easy to use.
Wonderful. Thank you. Just a reminder to all the attendees, please note down the contact information for our speakers, because you will not have the ability to download slides off of our website. And also, if you have any other questions, if you need further guidance on this topic, I'm sure they'll be able to help you out. So on behalf of Lab Manager, I would like to thank Agilent Technologies and PerkinElmer for their participation and support of this event. My sincere thanks to both our speakers today for putting in all the time and effort to make their presentations very scientific and very educational. So thank you both, Mustafa and Sam. The webinar will be archived on Lab Manager's website for 6 months. So do visit us online to review this webinar, to take a look at past webinars, or to get information about upcoming webinar topics. Thank you all once again for your time and attention. Until next time, goodbye and good luck.